Thank you, Juan, for the nice introduction. First, I'd like to thank the organizers for giving me the chance to give a talk here. It's a real pleasure. I've been following the One World PD seminar from its beginning, and I think it has been a great initiative. I have chosen the topic of my talk for two reasons. The first and more obvious one is the fact that this is my most recent work. I posted it in Arxiv several weeks ago. By the way, an updated version of the paper is available today because there were some minor mistakes. And the second reason is that this work has its origins in this One World PD seminar. Indeed, it was almost 1 year ago that I attended to a couple of talks here in this seminar, one by Daniel Peralta Salas and the other one by Francois Hamel. And those two talks piqued my curiosity. And so I started working. And so what I'm going to present here is the result of those talks. But before talking about mathematics, I'd like to share with you a claim that you may guess what it is. We all know about the dramatic events that are happening in Ukraine these days. And so I want to share with you my claim for this war to have an end soon. Let's hope so. Okay, the outline of the talk is the following. It's very simple. First, I'll give an introduction to the problem. And now into that problem, I'm going to give symmetry results. Actually, I'm going to discuss three types or three symmetry results for that problem. And for the proof of the last one, I will need to use the moving plane method, which is very well known, but I will remind it. Where we have nonlinearities which are not smooth, not Lipschitz continuous in particular. And I'll explain how and in which cases one can do that. So let's get started. So what I'm concerned in this talk is the existence of stationary solutions for the Euler equations. So the Euler equations is the equation that you have in the screen, where U is the velocity field and P is a scalar, is just the pressure. And I'm going to consider stationary solutions. That means that the velocity field does not depend on time. Moreover, I'm going to consider solutions which are compactly supported. That means that the flow outside a bounded region, it's not moving, it's quiet, and then in a bounded region it starts moving. Okay. And so this is the issue of my talk. And let me mention several things about the 3D case, because it has become very popular in the recent years. And because the question of the existence of any solution of this kind was not clear. Actually, I guess that most people thought that there were no solutions of this type. And there were some results in this direction. For instance, Hugh and Xin proved that if U is axisymmetric with no swirl, then the velocity field is zero. And moreover, another result is that if we have a generalized Beltrami field with finite energy, then U needs to be zero. It was proved by Nadirashvili and also Chai and Konstantin in a less regular setting. But quite recently, a non-trivial solution has been found, and this, I think it came as a surprise. It was a paper by Gavrilov in 2019, who built a C-infinity solution different from zero with compact support for the stationary 3D Euler equation. And this example has been further explored and improved and also extended to other fluid equations by Konstantin, La, and Vicol. A recent example of a solution which is discontinuous has been given by Dominguez, Vasquez, Enciso, and Peral very recently. But in my talk here, I'm going to consider only the 2D case, the two-dimensional case. So we are considering fluids that live in R2. And the existence of compactly supported solutions in that case is a much easier question. And let me show you why. First, let me write the equation in vorticity form, which is as follows. So if we call the vorticity is just the curl of the velocity field, then the equation reads as this. And of course, also the divergence of u is equal to 0, right? And yeah, so it tells you that the vorticity say that the streamlines of the flow are level sets of the vorticity. Okay. And moreover, another thing that one can do in dimension 2 is to use a stream function. Since u is divergence free, then u is the gradient, the orthogonal gradient of a certain scalar function, which is called the stream function. And for me, it's going to be called phi. So we have phi, which such that u is the orthogonal gradient of phi, and then the Laplacian of phi is equal to the vorticity. So when we plug the equation in vorticity form for the stream function, what we obtain is this relation, which tells you that the function phi and its Laplacian have gradients which are parallel. They always point in the same direction, maybe in different senses. Okay. And actually, as long as you have a solution of this question, you have a solution of the Euler equation, because you just take the gradient, the orthogonal gradient of phi, and you obtain a solution. Okay, so the question is, are there solutions of this kind? And the answer is yes. This is very easy. And one way to produce them is to look for symmetric examples. So think, for instance, of a radially symmetric function with compact support, okay, in R2. And you can make it C infinity if you want. And when you compute its Laplacian is also radially symmetric. And then because of that symmetry, their gradients point in the same direction. So it gives you a solution for the steady to the Euler equation. Okay. So this is an example, and you can build many examples like this, right? Because you can choose many different compactly supported radially symmetric functions. There is another thing that you can do is to add a couple of functions in this way. So a function being radially symmetric and another function being radially symmetric with supports without disjoint. And in this case, you obtain another solution. Observe that in all those cases, the functions are radially symmetric, so the level curves are circles. And these are called the streamlines, as I said before. So the streamlines are circles. So what we have is a fluid that outside the bounded region, it's not moving. But when you get close to the bounded region, then it starts moving, but it moves in circles. Okay. Okay, so the question of existence is clear in this case, in the 2D case. Here, where the natural question that appear here is if compactly supported solutions need to be symmetric, or if the streamlines need to be circular, or if you can find non-circular solutions. Okay, this is the main question that I want to address in this talk. Let me give some positive answers to that question. I mean, or let me discuss some positive answers to that question. And actually, as I stated, as I did before, I have not been able to find a specific reference telling you that under some conditions, the streamlines are circular. Okay, in the setting I mentioned before. There are some related results though, and I want to discuss them briefly. For instance, there are rigidity results on domains. If you have the fluid on domains with certain boundary conditions, then there are rigidity results. And there are many works by Amel and Nedirashvili. For instance, if the domain is a strip under certain conditions, then the flow is a shear flow. Moreover, if the domain is an annulus or a ball, they can prove that under certain conditions, the flow is circular, but they always fix a domain and some boundary conditions. The result that is most closely related to what I want to discuss today is the second one that I'm mentioning here, which is this one. So This is another result by Amel and Nadirashvili, who proved the following. Assume that you have a domain, which is an annular domain. An annular domain is just a domain with a hole, say. And assume also that the flow on the boundary is tangential, and also it has constant modulus, which is a constant different from zero. Well, if U is different from zero inside also in the domain, then they prove that the domain actually is an annulus and the solution is circular. Okay, this is so in our case, we want to, in a certain sense, extend this result for the case in which the flow vanishes at the boundary, which is we'll see that it comes with difficulties. Another related result is given by Gomez Serrano, Park, Shi, and Yao last year, and they proved that if the vorticity has compact support and is greater or equal than zero, then the straight lines are circular. But here is the vorticity which has compact support, not the velocity field itself. Okay. One could have wondered also about negative answers. I mean, constructions of non-radially symmetric solutions. And on that, there is a very recent result by Gomez Serrano, Park, and Shi. This was posted in arXiv in the last month of December, and they are able to construct a non-radially symmetric patch solution, which is also interesting in itself. So a patch solution is a patch vortex, which is a solution for which the vorticity is a linear combination of, in this case, three characteristic functions. And those characteristic functions are characteristic functions of domains, which are perturbations of concentric disks. And so, yeah, so this is interesting also because of the form, because patch solutions have interest in themselves. In collaboration with Pieralberto Sigbaldi, we are working in trying to produce another example, another non-symmetric example for this problem, but by using semilinear elliptic equations. In both cases, though, the velocity field fails to be C1. For instance, a vortex patch is never C1 because the vorticity is not continuous. Okay. So for C1 solutions, there are no solutions. I mean, there are no known solutions without symmetry. So yeah, so as I said, I'm going to discuss here some symmetry results. So I want to give you some conditions under which the streamlines need to be circular. Let's start with the first one. So we assume that we have a C1 solution of the Euler equations, and let's assume, and let's define omega, an open set, which is the set in which the flow is different, the velocity field is different from zero. I'm going to make two assumptions. First, U needs to be C2 inside omega. This is just a regularity condition. And the second one, which is stronger, is that omega is an annular domain, as I said before. So you have a domain with one hole inside. And yeah, and regularity is not really an issue here. We have put just continuous boundaries, for instance. Then we can prove that omega is an annulus and that U is a circular vector field. So this set omega needs to be around annulus, or the difference between two balls, and the solution is the streamlines are circular. Okay. So yeah, so I said that this assumption here is very strong, and the reason is that, for instance, it prevents the existence of isolated stagnation points. And a stagnation point is a point in which the flow is zero. And of course, you can have isolated points in this way, but under our assumptions, you don't have them. So U is zero only in the hole, say, and also outside the domain. Okay, so that's the first result I want to discuss with you today. And let me come to the proof. Wait a minute, because it's not, yeah. So the strategy of the proof is the following. It has two steps, and these I've learned this from the talks by Amel and Nadirashvili, actually. The first step is to prove that the stream function phi actually solves an elliptic linear problem. So, but here the function f is a nonlinearity and depends on the flow itself. This is the first step. And the second step is to try to use symmetry properties of solutions of semilinear elliptic problems to conclude. Okay. Okay, let's see how this can be done in our case. So first, the stream function is, let me remind you that the gradient of that U perp is equal to gradient of phi, or with a minus, I don't remember. So phi is C2 in the whole domain and is C3 inside the domain omega. Moreover, U is 0 on the whole and also outside the domain, and it means that the gradient of phi is 0 in those regions. So phi is constant in those two regions. So in the whole, you have a certain constant, C1, for instance, and outside you have another constant, C0, and yeah, and that's it. So those are two positive constants. Yes, so well, of course, the stream function, you can add a constant to the stream function and still have a stream function. And you can also multiply it by a constant and you still have a solution of your Euler problem. So you can assume that the constants are 0 and 1. So let me come with a picture. So I'm assuming that this is the domain that we are interested in. So it's an annular domain. And so as I said, phi, gradient of phi is 0 here and also 0 here. So we can assume that phi is exactly equal to 1 here and exactly equal to 0 outside. Okay. Moreover, U is not 0 inside omega, so it means that the phi has no critical points inside omega, and this will be used many times in our arguments. Well, the first thing that I want to say is that, for instance, phi cannot be strictly negative below, cannot be strictly negative inside omega or 0 inside omega. And the reason is that if phi becomes 0 or negative inside omega, then it has a global minimum inside omega, and that would be a critical point. And by assumption, this is not happening. Okay. For the same reasons, phi cannot be greater or equal than 1 inside omega. So phi is between 0 and 1 inside omega. Now I'm interested in the behavior of the level sets of phi. So the level sets, let me define them as phi c, and what I'm going to prove, wait, here we have 1, here we have 0, and what I'm going to prove is that for any c between 0 and 1, phi c is a connected C2 curve containing G0. So let me make a picture. So what I'm saying is that level set needs to be something like this. Okay. Let me show the proof of this. So first of all, remember that phi has no critical points inside omega. Then the level sets are smooth, are C1 or C2. So they cannot have crossings, nor things, and not weird things. And this implies that phi c, the level sets, is just a finite union of closed curves. This is the first thing. This is just by implicit function theorem. Okay. So the first step is that, the first thing I want to tell you is that those curves need to surround the interior, the G0, the whole of the domain. So the interior of any of those curves, gamma k, includes G1, sorry. And the reason for that is that imagine that gamma k has a curve like this. Then remember that phi is exactly constant on this boundary. And then we would have a maximum or a minimum which is achieved in the interior of omega. And this is again impossible because phi has no critical points. So this is not possible. So every curve has to surround the whole G1. This is the first thing. The second thing is that actually there is only one curve of this. So big N is equal to 1. And with this, we finish the assertion Okay, and the reason again is that it is actually the same argument. Imagine that we had two such curves. So let me depict one of them. So we have two curves which make part of phi c. Both of them has G0 in its interior, so it means that one of them has to be in the interior of the other, so as in the picture. And now I can consider the region which is between those two curves. And again, in the boundary of this region, phi is constant. So again, inside you would attain a maximum or a minimum, and that would be a critical point, and this is not possible. Okay. So this is not possible, and then it's equal to 1. So all level curves are connected curves for C between 0 and 1. Okay. Once we have this, we can already pass to a semilinear problem. So I want to define a function f such that minus the Laplacian of phi is equal to f of phi. So if I want to do this, the first thing that I want to tell you is that f of 1 needs to be 0, and also f of 0 needs to be 0. And why is that? This is simple because phi is constant here, but is constant equal to 1. But since it's constant, its Laplacian is 0. So f of 1 needs to be 0. And for the same reason, f of 0 needs to be 0. And okay, and how can I define f for any point c between 0 and 1? And this is easy because I just take c between 0 and 1. So I take any point in the level set, and the level set I proved before that is formed by a connected regular curve. I take any point of this set, and I define f of c equals a minus the Laplacian of phi at that point. And of course here, the problem of such a definition is that if f is well defined or not, because I have made a particular choice x in the level set. And the reason why this function f is well defined is because the gradient of the Laplacian of phi is parallel to the gradient of phi. So so in the level curve phi c, also the gradient is pointing orthogonally to that level set, and it means that the Laplacian is constant on the level set. So it's not really important which point do you pick in the level set. So this is how you define the function f. Of course, by construction, minus Laplacian of phi is equal to f of phi. This is just because I did it this way. It can be proved, and it's very easy, that f is a continuous function. This is not complicated. And the fact that f is C1, okay, it's not difficult, but I'm not going to get into the details here. But one can prove that f is C1 in the interior in the open interval 0, 1. And this proof requires two things. The first thing is that phi is C3. And this is why I made the requirement that the solution needs to be C2 inside. And the second tool here is that the gradient of phi is different from 0. With those two tools, you can prove that the function that you have defined f is actually a C1 function. But of course, the gradient of phi is becoming 0 exactly on the boundary values, and also on the values in which phi is constant, on the regions where phi is constant, and then this argument breaks down at the limiting values. Okay, but it's not only that the argument breaks down. The issue here is that f is not Lipschitz continuous, nor at 0 nor at 1. And the reason of that is the kind of solutions that you have. You have a solution which is constant on a region, and then it is different from constant. So and at that region, phi is equal to 1, for instance, and f of 1 is equal to 0. So you also have the constant solution 1. So that's telling you that the unique continuation principle is not working here. And if it's not working, f cannot be Lipschitz continuous. Okay, so it's not that f, we don't know if it's Lipschitz continuous or not. It cannot be Lipschitz continuous. This is, in my opinion, this is rather interesting because we departed from a solution which was completely, I mean, I assume only C2, but it could be C infinity, for instance. And you construct a function f, but the function f is not regular enough. Okay. So yeah, so we obtain a solution like this. It is defining all R2, a solution of a semilinear elliptic problem in this way. And now I want to prove that phi is really symmetric. So in what follows, I want to review some of the techniques that have been used in the literature to prove radial symmetry of solutions of semilinear elliptic problems. The first tool that I want to mention is the moving plane technique. Maybe this is the best known technique to prove radial symmetry for this kind of solutions. And however, this technique, if you want, has a look at the paper by Gidas-Nirenberg, for instance, or Serring, they always require f to be Lipschitz continuous, or Lipschitz continuous plus an increasing function. Okay. But in our case, this is not given. And I would like to say it's not only that this is not given, but actually the moving plane technique, or at least the classical moving plane technique, cannot work here. And the reason is, again, that you have a function that is equal to 1 in a region. But moving plane always implies that the normal derivative is strictly increasing. I mean, the function is strictly decreasing along the radius up to the center of the ball, for instance. Okay, so here you cannot obtain such a result. There is a moving plane technique for less regular functions f, and that was made by Dolbeau and Fellmer in 2004. And their technique allows the presence of plateaus. Plateau, when I mean a plateau, is a region in which phi is constant. And they are able to prove such a result for less regular functions f, but still they need to make some assumptions on the nonlinearity, and we cannot check if those assumptions are verified in our case. So we have not been able to apply those results. Another technique to prove a symmetry for semilinear elliptic problems is based on isoparametric inequalities and positive identities. And this was an original idea, very nice original idea of Lyon's in '81. And then actually it was made for the first time in dimension 2. And there were also works by Quesaban and Pacella, and more recently also a paper by Serra on that. And it only requires f to be continuous, or it can also handle some cases in which f is discontinuous. And so they need that the domain that depart from is a ball, and they can give you that the solution is radially symmetric, but they always require that f is greater or equal than 0. This is a common assumption in all those papers. However, in our case, just by integration, we obtain that the integral of f of phi is equal to 0. And this is just because this is a Laplacian, right? And phi is constant, is 0 outside a bounded set. And then f is changing sign, and then these arguments are not, I mean, we cannot use them. So actually I didn't know about that argument when I started working on this, and so I found it in the literature, and I found very interesting, which is another technique that was developed by Friedemann Brock in '95 and mostly in a paper in 2000. It is the use of continuous Steiner symmetrization. So here the idea is the following. So first, Steiner symmetrization is just to make a rearrangement, like Schwarz rearrangement, in one dimension. So basically you take an open set in dimension 1 and you transform it into an open interval of the same measure centered at the origin. Okay. And this is what is called the Steiner symmetrized function. What is new from the work of Brock is that he's able to define he's able to pass from the original function to the symmetrized function in a continuous way. So he can say build an homotopy if you want, where for t equals 0, you have your original function. For t equals 1, you have the symmetrized function. And then he computes the variation of the equation along this family of perturbations, and he finds a symmetry result that I'm going to describe now. And it fits perfectly in our city. I'm going to show here a theorem which is much less general than Brock's theorem, but this is enough for our purposes. So for us, f is going to be just a continuous function, and f a non-negative weak C1 solution of a semilinear equation in a ball with Dirichlet boundary condition. So this is posing a ball with Dirichlet boundary condition. Then phi is what he calls locally symmetric in any direction. This means that the domain omega is it can be written as the union of two sets. The set S is the singular set, is the set in which the gradient of phi is equal to 0. It's a set of plateaus, if you want. Okay, so the gradient of phi is equal to 0. You can think that phi is constant on the connected components of this set. Moreover, A is a countable union of radially symmetric domains, annuli or balls, and on those domains, the function phi is radially symmetric. So this is a Brock's result. So with a picture, what Brock's tells you is that a solution of a problem like this needs to have a graph as in the picture. You can have some plateaus here or here or here, but then you have some other domains inside, and there the function is radially symmetric. And this result is perfect for us. So how can we apply this? This is very easy already. So we just take a ball containing our domain omega. That's easy, because we need the function to be defined in a ball. And of course, it has the Dirichlet boundary conditions phi equal to 0. And recall that the gradient of phi is different from 0 in omega. So the singular set is just the outside of the domain and also the whole. So what it's telling you, what Brock's result is telling you, is that omega is the countable union of the sets AK. But those sets are radially symmetric, open, and disjoint. This is also a thing that I forgot to say. Those sets are disjoint and open. But since omega is connected, then you can have only one of those sets. This is by connectedness, and then omega needs to be an annulus. And phi is radially symmetric. And this concludes the proof. So a couple of comments on the proof. As you've seen, the ideas of the proof is very simple. It's just to pass a similar equation by studying the level sets and then to use the result of Brock. And the main ingredients have been the following. First, the lack of stagnation points inside omega. This is essential. If phi has critical points, as you know, then when you cross the critical points, then the level sets could be disconnected. You could have two curves. And then all thing breaks down, because you would have that the Laplacian is one constant in one level set and another constant in one level set. So it's no longer a solution of a semilinear elliptic problem. So the fact that we don't have stagnation points inside omega is compulsory if you want to apply a result in this way. And also the fact that omega is an annular domain has been essential in our arguments. And finally, we have used the symmetry result by Brock. Okay, so I want to present now another symmetry result, and now the idea is to try to put some obstacles to some of these ideas. In particular, I'm going to try to erase the fact that omega has the topology of an annulus. Okay, but of course I will change this with another assumption. Let me tell you. And this is the theorem B. Here I have stated it in domain omega in R2. Is assumed to be a C1 domain, and U is a solution of the Euler equation equations with U equals 0 on the boundary. Okay. We assume that we don't have stagnation points inside omega, and we also assume, and this is the strong assumptions, that we are going to assume the following. So U is 0 on the boundary. Maybe the normal derivative of U is also 0 at the boundary, or the second Neumann derivative, but at a certain point, we have a k derivative such that the k derivative, the k normal derivative of u on the boundary is different from 0. And this is different from 0 at any point in the boundary. So this is the strong assumption that I'm making here. Okay. So yeah, so this is the assumption. And of course, you need u to be ck in a neighborhood of the boundary of omega 2. Well, under this assumption, then again, we can show that the solution is radially symmetric. Observe that here, well, this is another thing I'll come to back later. I'm assuming that k is greater or equal than 2. So the first Neumann derivative, which is non-zero, is the second or higher derivative. I'll come back to that later. And if you do so, of course, the k derivative is different from 0, so the extension is not ck, but it's ck minus 1. This can be proved. So these solutions are ck minus 1 solutions compactly supported in R2. Okay. Okay, for the proof of theorem B, we can rely on all of that we know. So the only thing that is missing is the fact that omega is an annular domain. So this is what we want to prove. So the focus of the proof is to try to show that the topology of omega is that of an annulus. So a priori, you don't know that. So you have omega, which is a simply connected domain G0 minus a certain number of holes, Gi. Okay, and all those domains are bounded and simply connected. And so we have a picture like this. So I've depicted in this way maybe a domain with two holes, as you see. This is one hole and another hole. And then I define omega epsilon as the set of points which are at a distance to the boundary greater or equal than epsilon. And epsilon is going to be a small amount. So omega epsilon, the boundary of omega epsilon is the dashed boundary that is depicted in the picture. By regularity, if epsilon is small enough, you have a tubular neighborhood. So the boundaries do not intersect each other and they are regular. So you have n plus 1 boundaries and they are all regular. C1 in this case. What else? Remember that we have that the all derivatives were, or normal derivatives of u were 0 up to the kth derivative, and the kth derivative is always different from 0. From that, we obtain that the stream function phi satisfies such a condition, but with the k plus 1 derivative, because phi is, I mean, you have made an integration there. Okay, so you have that if you see what happens with phi on a line, on a normal line, at this point you have a certain derivative which is different from 0, and this implies that a little bit before you have a normal derivative which is different from 0. So what I'm saying is that if you take epsilon small enough, on this dashed boundary, the normal derivative of phi is always different from 0. Okay. And remember that u and the gradient of phi were orthogonal. So what I'm saying is that the velocity field u has always a tangential component. So u is never orthogonal to the dashed boundary. So it's as depicted by the arrows. So u cannot be orthogonal to the dashed boundary. It has always a non-zero tangential part. Okay. And yeah, well, from this, it's rather well known that such a vector field on a domain has Poincare index equal to 1. And this is just because I can make an homotopy to the tangential vector, to the tangent vector. And the tangent vector in dimension 2, it has always Poincare index 1. So the Poincare index along these boundaries, or this is always 1. And this is what is written here. And this is because the tangential part of u is different from 0. The Poincare index you can, or the Winding number, or the Brouwer degree also. Actually, I'm going to compute now the Brouwer degree in the domain omega epsilon. As you know, the Brouwer degree depends only on what happens on the boundaries. And in this case, the Brouwer degree of the vector field u in the set omega epsilon, in the set where we came a little bit inside the domain, is just the Poincare index at the outer boundary minus the Poincare indices at the inner boundaries. But I showed you before that all those Poincare indices are equal to 1. So we have 1 minus n here. And again, I use the fact that U has no stagnation point. So if U is not 0, then this Brouwer degree needs to be 0. And then we have that 1 minus n is equal to 0. That is that we have only one hole. And so our domain is an annulus, a topological annulus. And then we can repeat the proof as previously to conclude a symmetry. Okay. So I said before that we are assuming that the k derivative is different from 0 and k greater or equal than 2. What happens if k is equal to 1? Why I did this assumption? The last result I want to present is exactly this case, the case k equals 1. So this is our theorem C, and we need a little bit more regularity. U is C2 up to the boundary here. And U is equal to 0 on the boundary. We assume that U is different from 0 inside the domain. This is always our assumption, of course. And we assume now that the normal derivative of U is different from 0 at the point of the boundary. Then again, we can prove that the domain is an annulus and the U is a circular vector field. What is the main difference here? The main difference is that when we extend U by 0, now our solution is only continuous, it's not C1 anymore. So we are not falling in the setting of the first theorem I mentioned at the beginning. Okay, and we'll see that this comes with some difficulties. So as previously, we can prove that the domain is an annular domain. This is exactly the same proof, the proof of the Poincare indices and the Brouwer degree. Moreover, as previously, one can prove that phi is a solution of a semilinear elliptic problem. But now phi is restricted to our domain, to the closure of our domain, but not to the whole Euclidean plane. Moreover, phi satisfies this equation. So we have the semilinear elliptic equation inside omega. And on the boundaries, we have overdetermined boundary conditions. So we have Dirichlet boundary conditions, but we also have that the gradient is exactly 0 at the boundaries. So these are overdetermined elliptic problems. Moreover, f is continuous, but as I said before, is C1 only between 0 and 1 without taking the extremal values. And yeah, it's not necessarily Lipschitz continuous. So what is the problem now? Well, the question here is the following. If I compute f of 0, so how much is the nonlinear the function f at the point 0? So this is just minus the Laplacian of phi of x, where x is a point in the corresponding boundary. And it comes with the second normal derivative of phi, which by assumption is different from 0. So f of 0 is different from 0. And so, or in other words, when you extend u by phi by 0, you don't have a solution of a semilinear elliptic problem anymore, or you have, but f is discontinuous. Okay. And in the same way, you have that f of 1 is greater than 0. So here, you cannot rely on the result of Brock. Moreover, it's true that here we don't have this kind of plateaus because we are only in omega. We don't have anymore a solution in the whole R2. But so one could think that maybe f is Lipschitz continuous after all, but it's not. We can give an example of a solution in this way for which f is not Lipschitz continuous. So how can we deal now with this overdetermined elliptic problem? And this is the last part of the talk, and I'm going to use the well-known moving plane method. And so in order to introduce this, I'll first present some of the classic results in these aspects related to overdetermined elliptic semilinear problems, and then I'll come back to our setting. So this is the last part of the talk. The following classical result is due to Serring in 71. And actually, Serrin proved this when here we have f equals 1, but then it was extended to the case in which f is Lipschitz continuous, for instance, or Lipschitz plus an increasing function also. And the result reads as follows. We have a C2 domain and a solution of the determined elliptic problem like this. Then the domain is a ball and phi is really symmetric and decreasing. Many years later, Reichel and Sirakov gave a version of this for annular domains. So domains that have two boundaries. And so this is the result that they proved. This is the version by Reichel, actually. So again, f needs to be Lipschitz or Lipschitz plus increasing. And we have a solution of this problem. And we have Dirichlet boundary conditions and constant Neumann boundary conditions on the two boundaries. Then the domain needs to be an annulus and the solution is really symmetric. Okay. You can imagine that this is exactly the kind of result that we would like to have, because this is actually the setting that we have. The only thing is that our function f maybe is not Lipschitz continuous at the boundary points at 0 and at 1. Okay. So we are able to prove a version of this result which is suited for our purposes, and this is the next theorem. We think that this result is of independent interest, and it can be stated in any dimension. So there is no real need to be in dimension 2 here. So again, we have a C2 annular domain. Here we are in our setting, so f is continuous, but C1 only in the interior values. And we have a solution of the determined elliptic problem. We also assume that if the Neumann constants here are 0, then f of I is different from 0. And if you remember, this is exactly our situation when we came from the Euler equations. So this is exactly the situation. This is exactly the most intricate case. So this is the case that I'm going to consider in the proof. Then omega is an annulus and phi is really symmetric and decreasing. This is the result. So how can I compare this with the result of Reichel and Sirakov? Well, there is something. We have assumed this, and they haven't, but actually this is a byproduct if f is Lipschitz continuous. So this is not a real, I would say this is less general, this is more general, right? The f is less regular, so needs not be Lipschitz continuous on 0 and 1. But the strong assumptions I need is that phi is C3 inside in the whole domain, also up to the boundary. From the point of view of semilinear elliptic problems, this assumption may seem strange because I'm not assuming that f is C1, but I am assuming that phi is C3, right? This can be a little bit strange, but from the point of view of the Euler equations, this is exactly the situation that we have. Okay. So what is happening here is that phi is C3. So f of phi, f composed with phi is C1, even if f is not maybe Lipschitz continuous at the boundary values. Okay, so in order to explain the proof of this result, what I'm going to do is, instead of considering the case of the annulus, I'm going to consider the case of the Serrin problem. And so I'm going to review very quickly what are the ideas of the proof of Serrin and how can this be adapted to our situation. So the basic idea of the result of Serrin is the moving plane method, and I guess many of all of you have heard about this. And the idea is the following: we take an hyperplane intersecting the domain, and we compare the function phi on a cap and the function phi on the reflected cap. So if I define phi the reflection with respect to an hyperplane, then I define W as phi minus psi, where psi is the composition of phi with respect to that reflection. So I'm comparing what happens in a cap and in a reflected cap. So if I write the equation that W solves an equation in this way. So this is a linear elliptic equation where C of x, the coefficient, has this expression. Of course, this coefficient depends on the solution, but and this is the point where Lipschitz continuity enters. If f is Lipschitz, then C of X is an L infinity coefficient. And we know a lot of things of elliptic operators with L infinity coefficients here. Okay. So this is the technical requirements for the problem. And now the geometric idea, which is, as I said, so first one starts with an hyperplane, which is close to the boundary. And here it is easy to prove that in the reflected cap, phi is a little bit bigger than in the other part. So you can start moving your hyperplane, and you move and you push forward your hyperplane as long as W is still greater or equal than 0. And then you obtain a maximal value for that, and assume that this is the maximal value for that. And then actually what we have is that this is not the maximum value. And why is that? Because W is positive, so phi is bigger here than here. But by using the strong maximum principle for W, then W is strictly positive. And by using the Hopf lemma here, we have that the normal derivative of W on the boundary is non-zero. And this tells you that you can push forward a little bit more your hyperplane. So you can do that as long as your domain permits. And let me tell you exactly what can happen at the limiting value then. And there are two possibilities. One possibility is the case of internal tangency. That is that the reflected cap touches the boundary of the domain. In this case, we have W, which is positive in this region, but on that point, the normal, and here is where the overdetermined boundary condition comes into the play. Here, the normal derivative of phi and of its reflected is equal, so the normal derivative of W is equal to 0. And by the Hopf lemma, this implies that W needs to be 0, and this implies that the domain is symmetric with respect to this hyperplane. And then, well, of course, once you have symmetry, the direction is arbitrary, so it's symmetric with respect to any direction, so it's really symmetric. But this is only one of the possible cases. The second possible case is, as in the picture, it is the case in which the hyperplane touches the boundary in an orthogonal way. So in the picture, you cannot push forward anymore the cap remaining inside omega. And here is where the Serring idea came. First, he proved that the overdetermined condition implies that at that point, not only the first derivatives were 0, but also any second derivative is 0. This is the first thing that he proves. And another thing is that here you don't have Hopf lemma, because here in your domain you have a corner here. So here is the corner. So you cannot use Hopf lemma. But Serring proved a version of a Hopf lemma for domains with corners that tells you that it needs not the first derivative, but the second derivative to be 0. So if you have a positive solution of this operator L, where the first and the second derivative are 0 at the corner point, then W needs to be 0, and then the domain is symmetric. Well, so in the end, the whole thing is based on three things: on the operator L, which is the maximum principle, and actually you only need the maximum principle in small domains because you are always localizing what happens, and you also need the Hopf lemma and the Serring corner lemma, and those are very well known where C of X is bounded, is in L infinity. In our case, we don't know. Remember that F may not be Lipschitz continuous at the boundary, so C of X could be at the boundary value, so C of X could be unbounded near the boundary. But we have a control of C of X, and actually we can prove that C of X may be unbounded near the boundary, but times the distance becomes uniformly bounded. So C of X can blow up, but not at a higher speed than 1 over the distance. Let me skip the proof of this because I think I'm running short of time. And it's here where the C3 regularity of phi comes into the game. Okay, so now once we have proved that our coefficient is, well, it can blow up at the boundary, but you have a control. As far as I know, a maximum principle for such kind of operators like this with an unbounded coefficient C of X are known to hold for C in LP with P greater than N over 2. Observe that in our case, if C is equal to 1 over the distance, for instance, C is not in any Lebesgue space. So this is not applicable. Still, we can prove a maximum principle for small domains for such kind of operators. And this maybe this is known in the literature, but I have not been able to find a specific reference. The key idea for that is the Hardy inequality for sublevels spaces. And so this is the Hardy inequality. So phi squared over the distance squared, the integral of that is controlled by the Dirichlet energy. And here it is essential that we have here a 2, which is higher than a 1, right? And our coefficient is can be at most as 1 over the distance. So we have room for compactness and for estimates here. And this gives you a weak maximum principle in small domains, even in domains which are close to the boundary. With that maximum principle, we can just try to prove a Hopf lemma and a Serrin-Corner lemma, and they are based on constructions of solutions of certain problems. And so here the construction is as follows. We have a solution in an annulus, and the solution now I want to consider cases in which the coefficient is singular at the boundary, but as 1 over the distance. But this solution can be built and it's not difficult. And actually there is no real singularity here because psi1 is equal to 0 on the boundary. So here this is 0 and this is blowing up of order 1. And so in the end, everything is smooth. And actually the solution is C infinity. And we can build, this is a specific computation, one can explicitly compute a solution of this inequality in an annulus given R and given any constant C. And these are comparison functions that you use to prove your Hopf lemma to put it below your solution. You can do the same for Serrin-Corner lemma. I'm going to skip the details here, but the idea is that now you cannot use an annulus because you have a corner, so you have an annulus intersected with an hyperplane. And so let me take a section of this. So you find a solution of the same inequality as before, for which the second derivative along this direction is different from 0. And from this, you can prove a Serrin-Corner lemma. And once you have maximum principle, Serrin-Corner lemma and Hopf lemma, you can do the whole moving plane scheme. Okay, well, I explained everything here in the case of Serrin, but in the case of the annulus, of course, I have to do it in the case of the annulus, but the ideas are the same. Just a final comment, in the case in which the solutions have phi have plateaus, then their F is non-Lipschitz, and if one compute the coefficient C of X near the boundary of one of those plateaus, what one obtains is that C of X is of order 1 over the distance squared. So actually it's critical for Hardy inequality. So this is why, and one does not expect maximum principles for such singular coefficients. Okay, that's enough for today. I'm sorry for being a little bit late, and thank you for your attention.